Yeah, good afternoon to friends in Asia, and good morning to friends from Europe. And I'm not sure from Japan if people are there, so good evening. So really nice, and I'm very happy and very privileged to welcome Jairo Sinova. I think he does not need any formal introduction to this Spintronics community, such a well-known name. We read papers almost every week from him, new manuscripts, maybe more than one manuscripts every week. So anyway, I'm really happy, and on behalf of my team, Dr. Rajbhushan Singh, co-convener, my other team members, Puspendra and Shakti, Ajay and others, I welcome you, Jairo, and all the participants to this webinar series. Just for the benefit of the young students, I like to briefly introduce Jairo. Professor Sinova is working as an Alexander von Humboldt Professor of Physics at Johannes Gutenberg University at Mainz. After completing his doctorate at Indiana University in 1999, he became a postdoc at the University of Tennessee and at the University of Texas at Austin, before becoming a professor of physics at Texas A&M University in 2003. He has got many awards and honors, and just to say a few of them, he has received the Alexander von Humboldt Professorship Award, the Johannes Gutenberg Research Fellowship, the ARC Advanced Synergy Grant, National Science Foundation's Career Award, the Cottrell Scholar Award, and he was elected as a Fellow of the American Physical Society in 2011. His research interests are multifold. He's working on several things. A few of the research topics he's working. He's fascinated by the complex microscopic world of solids, where many things come together to create exotic effects that led to multifunctional materials with tunable properties. The ability to tune these properties fuels much of our technology today, and he works primarily in the field of spintronics, where the magnetic and electric properties of materials merge in new ways by using Einstein's theory of relativity, which acts as the link between these various properties. He aims at understanding the complex quantum world of solids with the long-term goal to better and more energy-efficient ways to process and store information. I think his topic today is very appealing about antiferromagnetic spintronics. So with this brief introduction, Jairo, I welcome you, and the stage is yours. And I just like to mention that during the lecture, we don't take questions. Kindly write your questions in the chat box or just raise your hand. And at the end of the lecture, we will take definitely one by one questions. All of those. Thank you. All yours. Please carry on.
Thank you very much. It's a pleasure to be here in this parallel, also very well-known series. I just realized that we mentioned about the spin-orbit coupling. I'm going to turn off the spin-orbit coupling later on in the talk. And this talk is about this emergent antiferromagnetic spintronics. I'm going to tell you a little bit of the story of now this hot topic that we've been part of leading, but in particularly I wanted to highlight here a young talent, a very young talented man, Libor Smekiel, that has been instrumental in leading intellectually these ideas. So these are his ideas. I'm just mostly a mouthpiece, like or most senior guys are. And my longtime collaborator, Thomas Jangworth, which has also been working tirelessly on these projects as well. I wanted to take a minute to, let me see, click, to make this talk. I wanted to be in honor, actually, of unfortunately a tragedy that happened recently. Dr. Uday Chopra, he was a student of mine for 5 years and became a doctor, graduated last year, and tragically passed away a couple of weeks ago while vacationing in Lake Lugano. Uday was a very valued friend and colleague of ours. He had a long life, a long love for climbing mountains, and he wanted to climb them all. And one of them was Mont Blanc, which I have a picture of, which I happened to take a picture a few weeks back. And this is in honor, so I'll dedicate this talk to him and his family during these tragic times. So the talk today, a little bit is in 3 parts. We're going to talk a little bit of introduction about antiferromagnetic spintronics and how we have learned from a spin-orbit torque in ferromagnets to propose a new novel thing that we did a few years back now, the Nail spin-orbit torque, which is a way to manipulate antiferromagnets electrically. And using that, we're going to merge two areas that before had not been merged before often, which was topological Dirac fermions and antiferromagnets and L spin-orbit torques. And the idea is how to manipulate Dirac quasi-particles electrically in an antiferromagnetic environment. Then we'll jump to actually predict new phenomena that has been predicted in some classes of anomalous or unconventional antiferromagnets, collinear in this case primarily. And we'll put that together in a discovery that we discovered, actually the Lieber Schmekel discovered, that by turning spin-orbit coupling off, you can actually now classify a new type of magnetic ordering that was kind of not recognized before, and now puts together into context many of the very recent discoveries in this very exciting area that is very rapidly evolving. Antiferromagnetic spintronics, now you may have heard several talks about it already. These are materials that are now becoming quite exciting. They have been known for quite a while. They were one of the last magnetic ordering systems to be discovered, of course, and they became prominent in the 60s and the 70s. They have very many advantages. They have non-volatile, radiation hard, like the ferromagnets. But unlike ferromagnets, they're insensitive to magnetic fields, and they have no fringing stray fields, which allows for very good scaling. They also have, instead of gigahertz dynamics, they have terahertz dynamics, which allows for ultra-fast switching. And this is inherited by this anti-exchange coupling, antiferromagnetic exchange coupling that unites the lattices. And they actually have been shown recently to have multiple stable domain configurations, which are very prone for artificial intelligence bit cells. And one of the other advantages that people may not realize, that antiferromagnetism, even though it was one of the last ones to be discovered, is one of the most ubiquitous magnetic ordering in our nature. Ferromagnets, the actual one that used in our technology, there's only 2 or 3 materials that actually are useful enough to actually make the magnetic memories that you're actually using today. But antiferromagnets, there's a lot more, and they're parent compounds from many things, from insulators, semiconductors, metals, and even superconductors, because they can live together. So one of the ideas that we came up with in a few years back now is to try to mirror the connection between ferromagnetism and antiferromagnetism, how to actually begin to manipulate antiferromagnets electrically. Antiferromagnets is, of course, their own property. The fact that they're insensitive to magnetic fields make them difficult to address, they're difficult to manipulate. In ferromagnets, we learned from the spin transfer torque and the spin orbit torque phenomena of how to actually switch some free layers by injecting spin currents through either polarizing it through another ferromagnet, or by injecting the spin currents through the spin Hall effect or the Edelstein effect, and being able to actually switch a ferromagnetic layer. These have led actually already to magnetic random access memories based on this spin transfer torque and spin orbit torque phenomena. And the idea was, can we actually do the same thing with antiferromagnets? The usual way, of course, it wouldn't really work, because if you just send a direct spin current into a collinear antiferromagnet, for example, you wouldn't directly see one part of the spins will actually counteract whatever the other ones are doing. But we could actually go back a little bit to the spin Hall effect, and in particular the spin galvanic effect, to learn how to do this in a particular antiferromagnet. The spin Hall effect, I think many of you may know already that study spintronics. You run a current, and perpendicular to this current, charge current, you have is a pure spin current perpendicular to that, polarized also within the plane of the current and the spin current. On the other hand, the spin galvanic effect is another effect, inverse spin galvanic effect, sorry, also called Edelstein effect. In a system where you have inversion symmetry broken, and many times both of them are occurring at the same time, when you run a current, you end up with a non-equilibrium polarization induced by the current perpendicular to the current again on the plane perpendicular to this broken inversion. Now, if you now try to think of antiferromagnetism, a system where you have a centrosymmetric system that is actually formed by two sublattices that each has opposite space inversion symmetry. And here we have the example of manganese to gold, where you can see here in the red sublattices and the blue sublattices, the gold is in opposite sides. And realizing that spin-orbit coupling, the thing that originates these Edelstein effects, is a local thing. It has to do with the locality, with electrons close to the core. Then you would realize that you can have within the lattice projected on the lattice, each sublattice bands will have opposite chirality of the form of the Rashba type in the plane, in the AB plane. The C plane is here perpendicular in this direction. Now, that means that if we run a current, in each sublattices, there will be an Edelstein effect. When you run a current to the right, as I draw here, you would end up with a perpendicular current, non-equilibrium polarization on the plane and opposite in the other one. And the important thing about that is that this would be within the unit cell. There will be this alternating non-equilibrium polarization that can couple to the Néel order parameter. Typically, of course, if you have something changing in the order scale of the unit cell, you would not see it experimentally, but here you do see it experimentally because you are coupling directly to the Néel order parameter. Effectively, what you do, you can think of this effect as having coils with different chirality, with different helicity in each of the sublattices. So here for the purple sublattices, you're coiling in this direction, and for the purple sublattices, you're coiling in the opposite direction. And that means that when you run a current, you will actually switch between by 90 degrees. And here is not, remember in antiferromagnetism, the difference is not between one direction and the opposite direction, but 90 degrees directions. And by running the current, you can actually switch the domains. This was actually the original experiment was done in copper manganese arsenate, which has a similar structure and science. And it was exciting because it actually occurred. I mean, here the years is of the publications, but the actual factual prediction and the observation was within 6 or 7 months or so. And then afterwards, it was also the material, the original material manganese to gold was grown here in Mainz by Professor Klaue's group. And the experiment was also shown where here you can actually observe the switching indirectly by the anisotropic magnetoresistance that you induce by switching the domains. But at the same time, I want to emphasize that these early experiments at low currents were done also at the same time as XMLD experiments that can actually directly show that the switching or the current switching is connected to the full domain switching of at the center. But when you go to larger currents, it turns out to be a different effect where you actually now it is not related to this Néel spin-orbit torque, but to some breaking up into micro domains that is being observed now when one talks about antiferromagnetic switching. So this was very exciting. This actually brought antiferromagnets as active elements of a spintronic of devices, and this is why from 2014 or so you may have seen that in many places new symposiums on antiferromagnetic spintronics. It's not that antiferromagnetics and the spintronics were not there before. It's just that they came together in that sense of active elements of materials. The next question that was natural to ask at the time is a question again by Libor Schmeichel. Can we actually put together Dirac physics and Néel physics at the same time? These are two areas, the Dirac physics and spintronics, this topological of graphene essentially, and the spintronics that had been in parallel in 2003. And it's not until 2014 or 2010 that things began to merge. And the key idea is that in this case, yes, the answer is a yes, that you can put Dirac fermions and antiferromagnetics, antiferromagnetic spintronics together because of the fact that you have two overlapping symmetry conditions to observe them. One of them is that you have two sites in the unit cell. In the case of the of the graphene, for example, is for the purpose of having a band crossing, otherwise you wouldn't have band crossings. And that here you need to have the two inversion partners, inversion symmetry partners, in order to see the nail spin-over torque. And another one, an important one, is the fact that you have to have PT symmetry being conserved. So P being parity on inversion, and TT being the time symmetry. In graphene, it comes directly because both P and T are conserved. But in graphene, it's PT that is conserved. The local parity is not conserved, and the T, of course, is not conserved because it's a magnetic order system. But both of them together, P and T, are conserved, protecting the Dirac points. So to show that this is the case, you can do a simple model. In this case, we first did a simple theoretical model where you have an antiferromagnetic with kinetic energy, kinetic exchange, and in this case, Kane-Meillet type of spin coupling, which has that property that of that inversion that still has this PT symmetry. Now, the key thing is that once you put it together, this effective Hamiltonian that I just showed has the property that if you actually now, the black line in here just represents the paramagnetic state of a simple model. The red line, it is the order state with the nail order parameter pointed along the 001 direction or parallel to that 001 direction. Remember that it's not really up or down, but it's just orientation. And then the other two on the right, the red and the blue on the right, corresponds to the nail order parameter being on the 100 orientation on the plane or the 11 orientation. And you can see that now you have these Dirac points being not at the X or N points, but shifted at different positions. And then depending on the orientation of the order parameter, of the 110, the different nail order, these Dirac points will open or close, so they will be massive or not massive. This is related to the fact that there's some protection. So whenever you have that, you have to have some protection or symmetry reason to have this protection of these crossings. And in this case, it has to do with non-symmetric symmetries, which involve a point root symmetry with a non-trivial translation. And here I can make the example of mirror symmetry that you have here, and remind you that if you have a spins, the spin perpendicular to the plane of the mirror, it will not be affected. So in this case, for example, if you now do the mirror operation with a half translation of the unit cell, so the mirror operation will bring this one here, that one there, and the same as mentioned here, and then you do a half translation, you end up with the same state. So that's a symmetry of the system, and that's the thing that protects your states between not being able to communicate with each other and maintain the crossing. Whereas if the orientation is not perpendicular to this mirror plane, this component, this one, the one parallel to the plane, will go up, so it will reverse, not the perpendicular to it. And then once you do the translation, this side and that side is not a symmetry, it's not the same, and you would induce the gap, for example. Of course, this is just a simple model, but the models are the effective models are just the low energy modes of real material that we want to search. And in this case, is copper, manganese, arsenide. In particular, the orthorhombic state is the one that we're proposing for this effect, because in the orthorhombic state, as compared to the tetragonal, you have most of the crossings here in the near the Fermi surface. And that's exciting from the point of view that here it can imply a very large change in resistivity depending on the orientation of the nail order parameter. So here you have, as you can see, the gaps closing and opening depending on the orientation, where it's 001 or 100 direction. This is important from the point of view of anisotropic magnetoresistance. So you could think of a device that running a current through the system, at least with low enough current and low enough anisotropy that is able to switch it, you would be able to actually induce a very large AMR. Notice AMR normally is of the order of a few percent, but here you can actually get it in principle to 50% at low temperatures, because you're effectively inducing and changing the gap of the system, as you can see here. Okay. Oh, sorry, let me go back so you can actually see it again. So essentially, you are, by the reorientation of the nail order parameter, you're essentially changing the the band structure close to the Fermi surface. In the case of the tetragonal case, these crossings are happening farther up away from the Fermi surface, and that will translate into weaker effects, typically, or observed at least maybe in the Hall effects. So this was this connection. This observation, unfortunately, has not been observed yet. The rhombic copper manganese arsenide is not easily grown as much, so we're still awaiting for that confirmation of the prediction. One thing that we pride ourselves is that we try to make predictions that are feasible, and hopefully this one will happen. Then we turn on to try to the next part of saying, okay, now we've learned how to think of some special antiferromagnets that, due to those symmetries, you can manipulate through nail spin orbit torques, orient the nail order parameter by currents. We've also learned now that not only that, in some of the systems now there's a lot of Dirac physics involved, and in some of them this Dirac physics will create a connection to the nail order parameter direction that you can, of course, manipulate through the nail spin orbit torque, and open and closing the gaps and change the resistivity very drastically that way. The next part is to ask questions of what happens in other systems, other antiferromagnets, collinear antiferromagnets, and in particular, an observation that was done recently, not too long ago, actually, by several independent teams, as included one of the first ones to propose to see that in a well-known antiferromagnet, ruthenium oxide, sorry, I don't have a name here written, it's ruthenium oxide that you see here, you actually have some colossal spin splitting of the bands. And this is rare in an antiferromagnet. This is actually something that one is used to seeing in non-collinear antiferromagnets, but it became a little bit of surprise in collinear antiferromagnets. Because in collinear antiferromagnets, and as I will describe later, you actually have the case that you expect just whenever your sublattices are connected by translation symmetry and a spin reversal rotation, that your bands will be Kramer degenerate. So there will be a spin degenerate. They're, antiferromagnets are really, really anti the ferromagnets. The ferromagnets are usually spin split bands. And the usual collinear antiferromagnets that we're used to will have the degenerate spin bands. But in this case, as you can see here, for example, in this portion of the variant zone, you actually have this very large splitting between the spin ups and spin down bands in this ruthenium dioxide. It comes from the fact that it is a collinear antiferromagnet, but you really is a crystalline environment that is actually the one that is confabulating with you to actually create that splitting. It has to do with the fact that if you actually just looked at the spin orientations and nothing else, just by the symmetry analysis of the spin orientation, of the total spin orientation, you will not be able to tell. You would think that this is a normal antiferromagnet. But if you look at the spin densities, and then you will see that this effective time reversal symmetry that happens in antiferromagnets wouldn't be there. One of the consequences for these bands is that this band in the antiferromagnetic, even without spin-orbit coupling, okay, so without spin-orbit coupling, you actually have a very large anisotropy of the orientation. Here I'm actually showing the Fermi Dirac, the Fermi surface of the spin ups and the spin downs, and as you can see, they're very much due to this this crystalline environment induced. The spin ups and the spin downs have different orientations, 45 degrees. So if you run a current in this direction, for example, to the right, you would actually end up with a spin current generated that has nothing to do with the spin orbit coupling, and that is very large Hall angle of 34%. This became a surprise to us. This is actually a connection, a work that was done by Rafael Gonzalez and Jakub Selesny, in connection with Lewis Mekel and us, where Rafael was doing the calculation, and she said, I'm turning off spin orbit coupling and I have a huge spin Hall effect. And I told him, and we told him actually it must be wrong. And of course he wasn't wrong. it turned out that this was due to this crystalline environment helping to create these large, huge spin currents that you can actually have in this if it was a single domain antiferromagnet. Not only that, the thing is that it is a different. This is a different effect in the normal spin Hall effect, the intrinsic spin Hall effect that we've shown before. It is a spin Hall effect. Typically, Hall current or Hall effects are due to interband transitions to essentially the reactive part of the response functions. Here, this is actually coming from the effects at the Fermi surface. So this actual will be proportional. It's a dissipative spin in that sense. But it's still quite large for a metallic system. And the exciting thing that just happened a week ago or 2 weeks ago, we received the news that the experimental verification by the Cornell group in this beautiful preprint that they posted, observing this effect that we predicted earlier this year. So essentially, as you can see, the pace of prediction and people paying attention and trying to reproduce these things and make them happen is very rapid in our community. Typically, from a prediction to a discovery, it is several years to prepare these things. We're talking, half a year to the most, which is actually very exciting. The area to be with. You never know what you're going to be working in a year from now because there's nothing discovered yet. Then one thing that, of course, this crystalline environment affords is that this splitting. I want to remind you that, of course, this is splitting. You're still an antiferromagnetic splitting, meaning that the total spin is zero. If you look at the splitting in here on the right of the system, you have the spin ups and spin downs. The splitting is opposite compared to the splitting in here. So the blue corresponds to one spin orientation, and the red to another one, and then it's opposite in the other sublattices. You end up with this, for example, close to the gamma point, to this dxy type of orienting symmetries, yeah. And these actually can be exploited, and then on the valleys, you're going to have a different type of splitting, and this valleytronics that is usually that you've heard in other environments. Valleytronics in this case have the usual case that for opposite spins, you have opposite momenta, you have opposite spins. So this red would be blue in here and vice versa. In this case, in our case in here, it's even in the momentum, which is red and red and blue. And that has several important consequences for possibilities of using these materials as colossal magnetoresistance and tunnel magnetoresistance devices. One of the things that you can do is essentially, when focusing of transport in these, for instance, metallic barriers where you have opposite nail orientation in opposite the devices. Of course, it would be difficult to create such a device. It would have to be thin layer and very controlled to actually control this orientation. But if you do so with a metallic barrier, so it would be giant magnetoresistance, by doing the calculation, essentially this part of the barrier zone would be the one contributing the most. And the calculation gives you a very large giant magnetoresistance effect, whatever 100%, at least a prediction. And I think there's several teams wanting to achieve this at the moment. These are also in the tunneling. This is done by Anna and Grace in our team, by now tunneling now in the other part of the brilliant zone, okay, and creating these tunneling barriers, again with opposite orientation of the nail or parameter. You end up also with very large effects of over 100, depending on when, of course, your Fermi surface is. This is quite important because up to this point, the idea of giant magnetoresistance and tunnel magnetoresistance in antiferromagnetic devices, it was unheard of. And if you manage to do this and actually couple these things, the scaling, because they're not now affected so much by large fields, can be amazing. So this is something that now I think this prediction was at the same time as a prediction by Simbal that I think has a similar paper at the similar time. That is once you realize that there's this spin split in these devices is important. And then another question that another anomalous thing that we understood is that in this particular case, you can also have a spontaneous anomalous Hall effect in these materials in a system that if you just looked at the magnetic orientation, you would think that there would not be an anomalous Hall effect. So anomalous Hall effect, which is the parent, of course, of the spin Hall effect, is a Hall effect that has been observed for a long time, initially, but it was a puzzle for a long time, theoretically. And in ferromagnets, it just means that you need to have a system whose symmetry allows for an axial vector. So, of course, in a ferromagnet, that comes from the fact that you have magnetization, and that's an axial vector, and therefore, by the symmetry, you will be allowed to have a Hall effect because a whole current is an axial vector. And in order to observe it to the Newman principle, you would have to have both. In antiferromagnets, it was realized in non-collinear antiferromagnets that you could have that. That is a symmetry that it would be allowed. But at no point, and then, these are, these non-collinear antiferromagnets, they're very nice antiferromagnets to play with, but a little harder to play with because this non-collinearity, it tends to be very strong in isotropy to actually reorient them. But still, it was a very exciting discovery proposed by Anna McDonald and then the team of Claudia Felser and others observing it. But if you ask the question, what about the spontaneous Hall effect in collinear antiferromagnets? Up to maybe 2 or 3 years ago, everybody have said, no, that would be zero. Because as I mentioned, if you just look at the orientation of the spins, you have this effective time reversal symmetry. Because if you make essentially a inversion operation from this point that I'm indicating with the pointer, you would switch the spins heights. So the blue will come here and the red will come there. And then you will now time reversal. So then you will flip the signs. And then that will give you effective time reversal symmetry, what we call tau antiferromagnetic symmetry. That's if you look at the spin environment, just the arrows for the total magnetization for each of the spins. But on the other hand, if you have a crystal environment that breaks the symmetry, so here's the non-magnetic elements, the oxygens in manganese oxide, that actually in ruthenium oxide, which I'm showing, not manganese oxide, ruthenium oxide that I'm showing here. The oxygen sites actually break that symmetry, and if you look at the spin densities, then you see that this symmetry is no longer valid. And then that creates an environment, a point group essentially, a symmetry point group, that allows for axial vectors, and therefore you will have a spin Hall effect, or anomalous Hall effect, sorry, depending now on the orientation of the antiferromagnetic order parameter. This is something that perhaps is very exciting. In a ferromagnet, you cannot turn off anomalous Hall effect because the magnetization is always there. It will be perpendicular to the orientation, and that's it. On the other hand, here, depending on the orientation of your annual order parameter, the symmetry group that you will belong will change. And that can actually allow or not allow for an axial vector, and therefore a Hall effect. This is what we call this type of anomalous Hall effect. This is in the family of spontaneous Hall effects. As a crystal Hall effect, similar to some other ones like topological one and the normal one have been connected to the origins of it. And then in this case, this of course has to do with the fact that you have this very anisotropic band structure even without spin-orbit coupling. And once you turn on the spin-orbit coupling, particularly at these crossings between the spin-ups and the spin-downs that you see here, there will be a large contribution from the various phase of the anomalous Hall effect. Of course, so in this case, if you turn off spin-orbit coupling, it will be a zero effect. But turning on the spin-orbit coupling, you end up with a very large anomalous Hall effect due to that essentially crystalline splitting that you see due to the crystalline environment. And if you calculate the Hall conductivity, you end up with very large contributions to the Hall conductivity, depending on the orientation, once again, of the annual order parameter. So the magnitudes are very large in record values, actually, compared to ferromagnets. one thing that I really need to emphasize here is that unlike the usual intuition with anomalous Hall effect that they say, well, you know, these are weak antiferromagnets. In reality, you have a little canting that it always comes along with these systems that allow for an axial vector to be present. So therefore, it was just going to be proportional to that magnetization is trivial. The case is not, because if you now turn on to be exactly compensated where there's no canting, you see clearly that first of all, the Hall effect will still be there. You have to take the limit of the magnetization going to zero. But you will be dominated, all of the contributions really coming from this crystalline Hall effect contribution due to that crystalline environment breaking the symmetry, and the magnetization contribution proportional to the weak magnetization of canting the spins is very minor. And then here you have about 330 sims per centimeter predicted to be, which is extremely large, whereas the actual magnetization is practically zero per unit cell. The exciting thing, of course, is that this one is also another one that has been observed. We've been trying now, I think, to do the experiments and convince the referees that this is an observed effect in ruthenium oxide. Here, the challenge on the ruthenium oxide is not to whether it's an antiferromagnet or not. That's been established by other works, but it's actually of determining which is the orientation that you see on the different films. But the actual magnitude that is observed is quite connected to it. In this case, it's not totally spontaneous from the fact that you need to apply magnetic field to reorient unilateral parameter, because here the symmetry orients in an orientation where the Hall effect happens to be zero as predicted. Another material is manganese 5 silicon 3, and in this case, one observes a spontaneous Hall effect, as you can see here. That is very present. We have zero fields with an enough reorientation. But here the challenge now is actually to really establish that the spin configuration, the magnetic ordering, is antiferromagnetic collinear, and this is what we're working on with a nice team of Vincent Blatt, Sebastian Koenenbein, and Helena Rajklova. And then in the last, I think I have, if I've been timing myself correctly, in terms of minutes, I have like 10 more minutes maybe to talk. I want to ask this question, and this is this interesting work that we're very excited about, which is altermagnetism. And this is the questions: are these discoveries peculiarities of just simply a few unconventional antiferromagnets, or do they point to something larger, something more important? The answer is more important. It actually turns out that we have been missing quite a bit of magnetism, because before we had ferromagnetism, where we know this is a clear where you have the splitting of the bands, as you can see here. You have a spin down, so it's majority band here, and a spin up, so it's a minority band. And then the usual antiferromagnets, if you just look at collinear antiferromagnets, you will recognize, oh, these are actually due to that effective time reversal symmetry, the fact that you have this transposing symmetry that can transpose from one spin to another and flip the spin, that guarantees effectively Cramer's degeneracy, and then also the fact that you would have a spin degenerate bands. And then this is to the, just to this effective time reversal symmetry that guarantees this for you can do by, in this case, by parity in connection with time reversal. If you actually do the play on the band structure, these connections, you will see that this is conserved, guaranteeing this degeneracy, that the spin ups and spin downs happen at the same momentum vector. Okay, this was directly analyzed in many works. But then there happens to be another problem. What if you actually this is not connected by a translation, but by a rotation in connection with a spin flip around the axis. And this was the concept of turning off spin orbit coupling and looking at the spin symmetries rather than magnetic symmetries. When you do magnetic symmetries, you have to reorient. If you do an orientation of your system, you reorient, you do the orientation, you do both spin and real space together. The concept introduced in Litwin in the 70s and others is to actually turn off spin-orbit coupling and do it in spin space and real space at different in a separate way, except for the fact, of course, that time reversal in the spin space will mean a spin inversion. And in this case, you have different type of symmetries. RS in here remains, it means a spin flip. I still have called it C2S in the new notation that we have in the new version of the paper. But it can come parity and spin reversal, the translation T and spin reversal, or spin reversal itself. That guarantees this collinear antiferromagnets. So if your antiferromagnets has these three symmetries, or just RS as a symmetry, spin flip, spin inversion as a symmetry of the system, that guarantees this degeneracy. And this would be the normal antiferromagnets. Now, what happens is that I want to make a point that magnetic groups and spin groups do distinguish something different. The point with magnetic groups that in here, you cannot tell whether you have a ferromagnet or a ferromagnet. If I tell you that you have this C2X symmetry in your system, like you have here, this has C2X symmetry, and this is a ferromagnetic order. Okay, and in here you're actually doing the change of axis. You're doing a C2 center 180-degree rotation of a spin and real space along the x-axis. So this will flip around, and this doesn't affect the spin. But if you do also when this antiferromagnet will be the same. So the fact that it has C2X magnetic group symmetry will not tell you whether you have a ferromagnet or antiferromagnet. On the other hand, if you now do the opposite, that you essentially connect C2X and the spin inversion together with a spin separate from the real space, this will distinguish, because if you actually now do the space first and then the spin inversion that gives you to this is not the same as that. So therefore, yeah, that doesn't have a symmetry. So C2X times RS as a symmetry will not be the ferromagnetic system, but it will indicate that it's an antiferromagnet, because if now you do the switching here and then you switch the spins, you end up with the same state. And this is the advantage of the spin symmetry groups, the spin groups, because they can distinguish between antiferromagnets and ferromagnets. And the key prediction here that we have is that there is a class, we're calling it, in this case, we're dubbing it altermagnetism, that actually connects, and it's a separate class that mathematically separated once you turn off a spin-orbit coupling. So essentially, you just have the spin symmetries, where 11, that connects these normalist point groups to the others, to the different operations in the spin space. So you have 11 belonging to the ferromagnetism, 11 belonging to the normal Kramer's antiferromagnet that has these degenerate spin bands, as degenerate bands. And these are the antiferromagnets collinear. Here we're specializing to collinear, by the way, where the C2 symmetry in spin space, here the notation, on the left of the double bracket is in spin space, on the right of the double bracket is in real space, is connected by C2, so flipping the colors. Here, remember that by having a spin up and a spin down, it's like having non-scalar, it's like plus or minus, or in this case, turquoise or purple. You actually, by connecting these two, by doing a translation and then a switch of the color, that is a symmetry. So the minute that these two are connected with a translation or inversion, you will be guaranteed to be in this group. And the other groups, there are 10 of them, so essentially a third of the fraction of the magnetic orientations, almost. It is when the two sublattices, this symmetry, which is considered a transposing of the two sublattices together with the flip of the spin, inversion of the spin, come together with a rotation. Or rotation as a translation. In reality, here for simplicity, we get rid of the translation, but the rotation has to be there. And if that is the case, that guarantees that there will be an alternating, equally spin and spin down in the system. But in this case, the spins, the ones that are degenerate, it will not be at the same or opposite vectors. Here, please keep in mind that this is not K and minus KY is not Kramer's. This is KY and KX, which is very different orientation. So in this case, for this example that I showed you here, which happens to be a real material, potassium, I'll show you in a minute, potassium magnetite, you actually have this inverted mustache look of the spin flips. And also remember that these are different orientation. Just as a summary of what I just said, is that here you have for the normal antiferromagnets, you have transposing, not transposing symmetries of the different sublattices. You have a spin polarization and exchange magnetization. In the other two types of antiferromagnets that now are split between Kramer's antiferromagnets and altermagnets, you don't have a magnetization, but you have an alternating spin momentum coupling in here. And here you have the symmetries will be parity times the spin inversion or translation times the spin inversion. And here we have rotation in the real space and spin inversion. The origin of the spin splitting, it actually is exciting to us. It's actually one thing that is quite an old prediction, that it actually comes from the fact that you have the crystal splitting of the material being confabulating to actually create this large splitting that you say. So the crystal fields are usually above the the magnetic order, so it's the potassium within the oxide. In this case, it's an environment where you have B and A sublattices. And here I'm showing you the projection of the bands in one sublattice or the other, showing this very large anisotropy between the two sublattices. And here the full band, where you hear this one is the crystal field splitting that is in this environment due to this anisotropic environment of the A and B sublattices. But the key thing is that once you actually turn on antiferromagnetism, you see that the splitting in one sublattice and the opposite and the other sublattice are in opposite directions. So this one will go, the turquoise go up, the purples will go down, and vice versa for the A sublattice. Okay, the A sublattice here, which translates, once you put these together in the non-projected normal band, to a spin splitting between purple and turquoise in different parts of the brilliant zone, okay, that are opposite to each other. So in this case, this one is originating, as you say, the spin splitting that you would observe is originating the magnitude from the magnetic crystal fields here. And of course, this one is exchange split from that one due to the normal exchange that is very large. The key thing is that here, the magnitude of these splittings compared to a normal spin-orbit coupling, which are very small, this can be very, very large, of the order of electron volts, which is actually very rare. And you have here, of course, this C4 symmetry that is still governed in the system. The important thing is that in this case, this is we can actually generalize it to the other point groups. As we mentioned, there's 10 point groups that give rise to this alternated spin-orbit splitting of the bands. I like to see that this is the typical thing that you see, this inverted mustache or mustache look like splittings with alternating signs. And keep in mind that this is the turquoise and the purple, and the purple and the turquoise in opposite parts of the brilliant zone. And we have here a family of candidates that range from insulators to metals to even here, that actually the one that we show here, this is lanthanum and copper oxide, which is the pairing compound of the cuprates. And you say, well, how come this has never been observed? This in reality, this will be degenerate in particular points of the brilliant zone or planes that are usually where the experiments are done. So I think the challenge is now to go away from those planes and try to observe this. And I think I'm on time, 46 minutes of talking. Just to show you, so you have this now predicted. I think it's exciting. Before we have ferromagnets, we have antiferromagnets. Now, by turning off the spin-orbit coupling and seeing that the dominant symmetry is due to this crystal environment, you can actually clearly specify a new class of magnetic ordering which is, of course, you're splitting the antiferromagnetic family into these two, the Kramer's antiferromagnets and the altermagnets, that have very different properties. And in particular, this is spin momentum locking due to the crystal environment that you can have in these systems. And the fact that they're connected to even the superconductors could be exciting and part of the family. So with this, I think I've given you an overview of, I think I've covered too much, probably a lot, but my idea, my focus was to show you how exciting all of these things that I've talked about. These are only recent things. These are 3-4 years of actual very hard work that is very rapidly prediction, discovery, experimental prediction, etc., that is coming together. That brought us from, of course, the spin Hall effect that has been around for a long time, understanding the spin orbit torques that we actually know in ferromagnets, and utilizing in these two parts of the talk is what I've talked about, of predicting and observing the L spin orbit torques, connecting them to Dirac quasi-particles and their manipulation, and beginning to see this anomalous transfer behavior in these unconventional antiferromagnets, like lithium oxide and others, and that realizing that they belong to a new class by turning off a spin orbit coupling, this connection between the spin and the charge, realizing that symmetry was always there, and that can define a new type of class that will be easier. So we have to go back to the materials and classify them within this classification to realize which one has the potential for this type of physics. And with that, I thank you for your time, and I'll take your questions. Let me go back to, how do I do this? Did I turn on the thing again? Okay. Right. So
thank you very much, Jairo, for this excellent overview of this. And I think it's time we take a group photo, then we'll come back to your question answers. So okay. May I request you to stop sharing, and
yes.
I request everyone to switch on their camera.
Yes, even my students are sneaking on there.
Yeah, very nice. So I will go for the gallery view.
Yeah, right. Take a picture.
All right. So I'm taking a good photo now. Smile.
Excellent.
One more.
I think they will come in slowly.
Yes. Okay. Still, many people have not switched on their cameras. Okay, it's their choice. Thank you so much. So I think we can stop our cameras, and Jairo, you please share your screen again, and we take some questions now.
Yep. So let me share that, and then so go ahead and ask.
Yeah. So I see. Okay, Burkhard has.
I think Burkhard has a question, so you can take Burkhard's question first, maybe.
Yes, please.
I do have a question. Thank you very much, Jairo, for this very nice overview. Coming to this altermagnets, can you speculate about the dynamic excitations in this material, in these materials?
The dynamics, meaning in the terms of excitations of the type of spin wave.
Harmonics branches, because I mean you showed by yourself how important all this antiferrometric modes are and so on, conventional antiferromagnets. Mm-hmm. So what about these new altermagnets?
In the altermagnets, the magnetic order is still very much the normal collinear antiferromagnets. So I don't expect that to be too different from the magnonic point of view in terms of the antiferromagnets. There will be, of course, some when there's a strong magnon electron coupling, you could have some differences in the particular orientations. We haven't really studied that at all. We've been focusing a lot more on the electronic part of the environment, but this we still consider in this case to be. If you look at them, you would think that this from the orientation from the magnetic excitations. You would still think of these guys as collinear antiferromagnets. Like if you ask this question to Helena, to Helena, she would just say, "Oh, in my phenomenological approach, the two would be the same."
Yeah. So probably no fingerprint in the top.
I don't want to say no, because of course I've been wrong so many times on these things. Libor will come and tell me, oh, but there's this exciting things. And then actually with Alexander Muk, maybe I should talk about it, that actually this could be connected. And it wouldn't surprise me that you could connect, because you see, here you have these D waves and all these things in the crystal, due to the crystalline environment and due to the electronic environment, and that there will be a coupling. Yeah. The question is how strong that would be and in where you would actually observe it. So that's the answer, that we don't know what it would be. I mean, there could be some differences, but I don't know how strong that would be.
Thank you.
Yeah. So there was some question.
Yes. Before I go to Priya has a question, but I have just actually kind of extended question to what Bukat has asked about this altermagnets. It's very interesting. Like ferromagnets, we have Curie temperature. Antiferromagnets, we have Nel temperature. Do we expect some kind of transition temperature for the altermagnets?
No. The ordering is still Nel order. Nel order, from the point of view of ordering and exchange, is still antiferromagnetic exchange.
Okay, it's a kind of subgroup of antiferromagnets. That's what you want to say?
It is a group. I mean, you think of it as before it would have been, or you could consider them to be antiferromagnets, but they have properties that the usual Kramer's degenerate antiferromagnets don't have, nor the ferromagnets have. So they have these alternative, particularly in the electronic structure, which is the most important one from the device point of view. They are very different. And in the sense that's created due to the crystalline environment that comes along with it, that it was not recognized because, as I mentioned in the magnetic analysis, magnetic group analysis, which is very powerful, it was all together. You couldn't disentangle anything. So you could say, okay, there's a splitting, but I don't know if it's due to spin-orbit coupling or to some other things. And the idea that you can actually now identify with these very large splittings that can give you colossal magnetoresistance and things like that, it will be in the electronic response that you actually see it in the antiferromagnetic ordering. Particularly these collinear antiferromagnets should behave very similar. And in fact, many of these, of course, are non-materials that before you would have said that's an antiferromagnet, because that's an antiferromagnetic order, Nel order parameter, normal social stability for the antiferromagnets, etc. And they were not. Some of these materials, of course, they were always there. They were not identified as altermagnets because you were not looking at that band structure in those splittings that you would have been surprised. You would have not expected it. So because there's never an expectation of it.
Okay.
They were kind of hidden in plain sight, if you like.
Okay. So I'm sorry. I mean, this is very new to me, and so maybe I'm asking very stupid question.
No, don't worry. It will not be as stupid as I expect questions, because Libor is the one that has been teaching me about all of these things. Yeah.
So how do we distinguish conventional antiferromagnet and altermagnets? So, like, what would be the way?
The teaching, and I should actually emphasize here, is here. A conventional antiferromagnet collinear, let's talk about collinear, is the one that the symmetry, if you turn off spin-orbit coupling, the symmetry is that there is a transposing symmetry that you transpose the sides, the sublattices. So here there will be, just in this case, for the example simple example that I show here, that there's a translation together with a change of color. So if I actually translate these sublattices to these sublattices and I change the colors, that's a symmetry of that one. So if you have a transposing symmetry that is a translation or an inversion together with the change of the colors, that will guarantee to be what is called Kramer's antiferromagnet. It will guarantee that all of your bands are spin degenerate, okay? That you don't have any splittings at all. Now, the altermagnets, and this is, I was probably too fast on that, is the one that in here, for example, in this one, because of this tilt that you see here on the environment, this is actually the lanthanum copper oxide. This is the pairing compound of the superconductors. You have a C2. C2 in this case is the spin. In the spin is a change of the colors of the spin, so the purple to the turquoise, together with the rotation, but only together with the rotation. Yeah, so you have to rotate this one to this, so you rotate here to this one and change the colors. And if the transposing symmetry is a rotating symmetry, okay, then you will be guaranteed to have these splits. Because essentially what guarantees is that you are connected not to the same momentum and the spin, but to a different momentum that it doesn't have to be. It is connected by those rotating symmetries, but it's guarantee you, first of all, that you have a perfect antiferromagnet, but it's also guarantee you that you have a spin split in parts of the Berlin zone.
Okay, so that means, okay, I'm sorry. So that means from an experimental point of view, to understand the spin structure and the symmetry, one has to do some kind of neutron scattering?
Well, not neutron scattering, because neutron scattering is more about the orientation of the spins, and the spins will be still collinear. Okay. Here you would talk about ARPIS, for example, where you would actually do an ARPIS, and then you would see the spin result ARPIS, you will see for the first time in an antiferromagnet is spin split bands, which you would never expect. And I mean, if you actually, most of the, you know, if I asked you 2 years ago or so, what do you expect from the ARPIS, from this spin resolved ARPIS, from a collinear antiferromagnet, you would say that would be the most boring thing in the world because they're spin degenerate.
Yeah. And
then now you're going to see these spin splits. But also keep in mind that, you know, you would never see, for example, giant magnetoresistance or colossal or giant tunneling magnetoresistance in an antiferromagnet because of the spin degeneracy of the bands. And then if you make this antiferromagnet zero magnetization, yeah, that you can control the orientation of the nail or a parameter somehow. Okay, that's a different challenge. You would also see giant magnetoresistance in a system that has zero magnetization, total zero magnetization. And this, from a device point of view, if you manage to do it and control it, it is huge.
Okay, so the lower, actually the band diagram is experimental or systematic?
No, this is theoretical. This is a theoretical prediction. You know, I'm a theorist. In spite of the fact that half of my papers are with experimentalists, yeah, I'm a theorist at the end. But I think we have a good record of predicting things that do happen. You know? Okay. The intrinsic spin Hall effect was one. Nail spin over torque is another. And so far, and then actually the exciting thing, by the way, this is actually not this prediction, because in ruthenium oxide is on that family. And this prediction of this electrical spin splitter, of this spin Hall effect, dissipative spin Hall effect in a sense, has been, you know, take a look at this. We just saw it a week ago, and it's very exciting because this actually is also a smoking gun of that. You would never have that in a normal system, yeah, in a normal antiferromagnet. Yeah.
All right, so then we are ready to see the experimental verification of those altermagnets. Yeah.
No, and I think also one of the questions we have for one of the referees that's still battling with is the fact that if you actually ask the questions like, well, you know, if you say that this was in lanthanum copper oxide in the parent compound, this should have been seen already. And it's like, yeah, but the problem is that if you analyze this and you look at where they all have all the experiments, is exactly in the planes where it is a spin degenerate. Okay. I mean, this is a part of the Berlin zone. Remember that this is not like normal ferromagnet with the whole band, one goes down and one goes up. Here is alternating in the different parts of the Berlin zone, and in some parts it is degenerate. For example, you're guaranteed that in the gamma point and in the high symmetry lines, you will be spin degenerate. It is at different parts of the Berlin zone that you're not.
Okay, thank you so much. Priya, I'm sorry that I took so much time. You can ask your question.
Oh yeah, okay. Thank you for the nice talk. Actually, my questions were some naive questions regarding this altermagnetism that you're talking about. So you talked about spin momentum, a form of spin momentum locking without any spin orbit. Right. So I have some naive questions. So for instance, if you take the transition metal dichalcogenides, which also have the spin momentum locking, and you have this, you know, the spin splitting for a monolayer opposite at K and minus K. So do you have to
the spin orbit coupling, right? You know,
yeah, that's to the
spin orbit coupling. The other one is not.
Yeah, that's true. So the question is, do you have a similar one whereas over there it's K and minus K, there the spin momentum locking leads to, you know, certain scattering mechanisms to be things. So in this case, would it be something similar?
So that's one of the smoking gas. It is different. I mean, the point is that, for example, because this is due to this crystalline environment, the fact that it's actually connected to the crystal, that you have this evenness in momentum. The one that you mentioned, of course, I think I'm very familiar with, of course. Spin-orbit coupling is my love child, I love it. I love this thing, and that will guarantee this oddness, since the spin valoritronics that is called, you have the opposite momentum, opposite spins, the same with Rashba, the same with Dresselhaus. This spin-orbit coupling connects with opposite momentum. You are guaranteed to have an effective field that is opposite. In here, it is actually the evenness that is the different. If you actually look at here, let me take a look at this slide. Where are we here? The best one is here. If you look at these valleys, this is from, I think it's in the paper. I don't want to say which, could be ruthenium oxide, but I don't think so. I think I have to look which one is the actual compound. But in this, in M2 and M1, the points in the Berlin zone, these are actually calculations. You actually have even in momentum. So K2 minus K, you still has the same spin orientation, but totally zero. Yeah, the total is zero. But this would be something that you would never have with the spin-orbit coupling. Another important thing that is actually very important is the size and the scale. If you look at the spin-orbit coupling tends to be of the order of milli-electron volts. This has to do, of course, with the fact that electrons are moving around 100 the speed of light in our environment, as the Fermi velocities, and that tends to be this 100 tend to be the scaling that you actually have of the spin-orbit coupling energy or relative to the electronic energies. So, if you go from electron volts are electronic structure energies, and milli-electron volts, 100 at most, are of the spin-orbit coupling. Here, because the splitting that I showed you here, I was trying to make that case in here on the very potassium ruthenium oxide. That's actually originating from the crystal fields, which can be very large. So the fact that you would have these huge splittings in that environment with this huge spin momentum lock-in, that's also another thing that would never occur in the spin-orbit coupling.
True, but what kind of spin momentum locking, what kind of symmetries can I think of in this context?
Here's in the table. Sorry, I didn't.
No, I meant in the the transport, for instance, or signatures over there. That's what I meant. Like, I understand the symmetries you're showing over here, but could it lead to something similar where some kind of certain channels or certain enhancements or something?
I think the anisotrope, the magnetoresistant magnetic, the anisotropic magnetoresistance, for example, would be quite affected by that.
Okay. And so, one last question is this. I mean, so for instance, if I okay, so you spoke about the evenness over here, but suppose I put spin-orbit interactions over here, how does the scenario change? Because
perfect, that's a great question. Thank you very much. I think I'll pay you later. So if you actually look at these two here, B and D, one is without spin-orbit coupling, the one without spin-orbit coupling, you don't see any difference because spin-orbit coupling is a very minor effect here. The key thing is, one of the important things is that we have been when you turn on a spin-orbit coupling, you couple the two environments, the spin, the symmetries, and the symmetries, when you turn that off, you have more symmetries. When you couple them together, you have more symmetries, and this is similar to saying, I think I have a picture like this. Let me actually show you this picture, and if you actually see here, do you see this Fermi surface, the one of the A and the B?
Yeah, yeah.
So the one of the A has actually fourfold symmetry. The one of the B does not have fourfold symmetry. It looks to you like it has, like you would recognize it as fourfold, but it really does not have it because of a spin-orbit coupling. And this is the problem when you look at symmetry from that symmetry point of view. The symmetry is just absolute, yes or no. It doesn't tell you how much of the break-in is. Is it really like mostly fourfold symmetry, but then it looks a little blurred? And in this case, once you turn off spin-orbit coupling, you would not predict from the magnetic symmetry analysis that type of symmetry on your Fermi surface. Whereas if you actually look at an experiment, you would swear to it's like, okay, just due to the resolution, that looks like 4-fold symmetry in B, but it's not. It's actually 2-fold symmetry. And this is the point that sometimes the spin-orbit coupling, of course, for things like Hall effect, anomalous Hall effect, and things like that, this is the origin. Like, without it, you wouldn't have it. But often, for effects that are just small corrections, like usual transport of anisotropic magnetoresistance or things like that, they're just often very small corrections. And if you actually look at what happens if you actually compare the calculations with and without spin-orbit coupling, they look identical. I mean, here you can see here in this bands, this is projections of the bands. So this blues and here this is a projections because the spin is actually a quantum number up here and it's not in here. But you can see that there's only some splittings here that are different and way below. But for the ones that are crystal dominated, magnetic crystal field dominated, there's no, you will see only if you zoom here and there that you will see small changes.
Okay, thank you.
Thank you. That was a great question. Thank you.
Thank you, Priya. So there is a question in the chat box by Sriram. I'm reading it. Can you please explain briefly how non-equilibrium spin accumulation reverse the magnetic order parameter in antiferromagnetic? Does it involve any higher order spin torque other than conventional damping-like and field-like torques? Okay, so that's a very nice question. So this is connected to this effect, to the Edelstein effect, where in the Edelstein effect, I hope you understood what I said, that if you run a current and you have a spin-orbit coupling, like of the Rashba type, you would end up with a spin accumulation perpendicular to your current. Now, this happens when you have broken inversion symmetry. So, the broken inversion symmetry in this direction, and then the current is in that direction, and perpendicular to that, you have the current. So because now you have the two sublattices, each sublattices, you should think of it as a Rashba-like broken inversion symmetry sublattice. Like if you actually if you could look at the spin with the RPS or some of the tools, result in the per sublattices, you would actually get this chirality and this other chirality for the other sublattice of this spin hidden, I think Zunger call it hidden spin textures. Yeah, but when you run a current, that will mean is that there will be a spin accumulation here on one sublattice and the opposite, and that will couple it will be effective like an anisotropy. It will be a field-like. I mean, if you want to think of a field-like, but be careful. I wanted to give you an idea that field and damping-like in ferromagnets, it doesn't translate to field and damping-like in antiferromagnets. The dynamics, as I was taught very clearly from my beginnings in antiferromagnets by Helen Gomonai, are very different in one beast than another. Many times the intuition that we bring from ferromagnets doesn't really translate to the antiferromagnets. But in here, it translates fairly well. It is like having a current-induced anisotropy. So in this case, if I run the current, the nail order parameter will want to be perpendicular to the current, because perpendicular to the current, you have these opposite sublattices. And this is what I show here, that it is almost as if I was coiling the different coil directions with your current and the different sublattices. So if I run a current, in this case, for the orientation in this one that I'm pointing here, the current is running like this, in this direction. And if I run it in the other cross, it will actually flip. And of course, for these experiments to work, you have to have an antiferromagnet that itself has a low anisotropy, on plane anisotropy, such that you can overcome this anisotropy by the current before it becomes too hot. Yeah. So I hope that helped. Yeah, thank you so much. So if you could kindly stop your screen, I like to share my screen to give present a small token of appreciation. All right. Do you see my screen? Yeah, I can see your screen. Oh, look at that. Okay, so it's a digital plaque. Well, we would be very happy to welcome you someday physically at NICER, Bhubaneswar, in our institute in India. But I don't know when it will happen. Let's hope near future. Yeah. Nevertheless, so on behalf of our team and from NICER, we would like to present you this digital plaque. So I just read it for you. W2S seminar webinar series on Spintronics. Naisal, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Jairo Sinova, Johannes Gutenberg University at Mainz, Germany, in recognition and appreciation for being a very valuable speaker to give a lecture on emergent antiferromagnetic spintronics from Dirac quasi-particles to non-relativistic novel magnetic classes. Thank you so much, Jairo, for your excellent talk.
Thank you.
Everyone. We really enjoyed very interesting topics. And obviously, I have not understood everything.
It tends to be a bit too much, maybe. I have to cut it down, I think.
Yeah, I mean, your lecture was nice, but these topics, the concepts are new, so we need some time to digest. But thank you very much for bringing this.
So very nice questions from everybody. Thank you very much.
Thank you. Yeah, see you next week in the TMA conference. And next week, Professor Kenji Uchida from NIM Tsukuba, Japan will give the talk on spin caloritronics.
Yeah.
So I hope to see you guys next week, same time, same day. Thank you very much. Please stay safe. Bye-bye.